You know, Maya, we often talk about how much we don't know about various topics, but today's subject feels particularly insidious because it's about something potentially happening inside us that we're completely unaware of, silently impacting our health. We're diving into a groundbreaking new discovery that suggests your own brain could be inadvertently raising your blood pressure, and you might not even realize it.
That's such a fascinating and, frankly, a little bit terrifying premise, Alex. It's like our own internal system is working against us without our conscious knowledge, which feels like the ultimate things I know nothing about scenario. This new research really challenges a lot of what we thought we knew about hypertension, moving beyond just the heart and vessels to a much deeper neurological root cause.
Absolutely. So let's set the stage. A study published just recently in March 2026 in the journal Circulation Research has pinpointed a very specific region in the brainstem that appears to act as a direct trigger for high blood pressure, or what medical professionals call hypertension. This is a significant shift in perspective for a condition that affects so many people worldwide.
And the name of this particular region is quite a mouthful, isn't it? It's called the lateral parafacial region, or PFL for short. What's truly intriguing is that this area isn't just some random part of the brain, it's primarily known for controlling very specific and forceful actions, like when we have to cough vigorously, laugh really hard, or exert ourselves physically during intense exercise.
That connection to forceful exhalations is really what grabbed my attention. The research indicates that when this PFL brain region becomes activated, it doesn't just manage breathing, it also stimulates nerves that cause blood vessels to constrict, leading directly to an increase in blood pressure. It's a direct neural pathway to hypertension, which is quite a revelation.
And the most compelling piece of evidence from the study, at least in their initial animal models, was that when researchers managed to inactivate this specific PFL region, the blood pressure levels in those models actually returned to normal. That's a pretty strong indicator of a causal link, suggesting this isn't just an association but a direct mechanism at play.
That's a critical detail, Maya, because it moves beyond correlation and really points to causation. For decades, our understanding and treatment of hypertension have largely focused on factors like the heart's pumping efficiency, the overall health and elasticity of our blood vessels, kidney function, hormonal imbalances, our dietary salt intake, chronic stress, and of course, genetics. All of those factors are undeniably important, but this new finding introduces a fundamental direct role for the brain itself in initiating and sustaining high blood pressure.
It truly broadens our understanding, adding another layer of complexity, but also offering new avenues for intervention. The lead researchers on this particular study are Professor Julian Payton, who is the director of Manaaki Manawa Center for Heart Research at the University of Auckland, and Professor Davi Jose de Almeida Moraes from the University of São Paulo. Their collaboration across continents really highlights the global effort involved in such significant scientific breakthroughs.
It's fantastic to see that international collaboration driving such important research. Now, let's delve a bit deeper into the brainstem itself, because for many listeners, that might sound like a very abstract part of the brain. The brainstem is actually an incredibly vital control center, often called the oldest part of the brain in evolutionary terms, responsible for all those automatic bodily functions we don't consciously think about, like breathing, digestion, and maintaining a steady heart rate.
Exactly. It's the brain's autopilot system, essentially. In the context of blood pressure, the brainstem plays an absolutely crucial role in regulating it by integrating signals from various other brain regions and the autonomic nervous system to maintain what's called cardiovascular homeostasis. When something goes awry within this incredibly complex network, it can significantly impair our body's ability to regulate blood pressure effectively, thereby contributing to hypertension.
And it's not just this one study in 2026. Recent research has been steadily building a stronger case for the brain's intricate involvement in hypertension. For example, a January 2025 study highlighted associations between the microstructural integrity and myelination of the brainstem and a person's hypertensive status. This suggests that even subtle damage or changes in this region's structure could be a contributing factor to elevated blood pressure.
That's a really important point, Alex, because it implies that even before we see overt symptoms, there could be subtle changes happening at a cellular level within the brainstem that are setting the stage for hypertension. Another study from February 2026 actually identified specific nerve cells within the brainstem that function as a kind of stabilizing system for blood pressure, preventing those moment-to-moment fluctuations that our bodies constantly manage. If these cells aren't working correctly, it can lead to unstable blood pressure, even if average readings might still appear normal.
It's like having a faulty thermostat for your body's pressure regulation system, and the issues don't stop there. Brainstem hypoxia, which means low oxygen levels in the brainstem, has also been implicated in the development of hypertension. The theory is that this lack of oxygen can increase sympathetic nervous system activity, pushing the body into a more constant fight or flight state, which naturally elevates blood pressure.
And we absolutely cannot overlook the well-established link between chronic stress and hypertension. We've known for a long time that chronic stress significantly increases sympathetic nervous system outflow, leading to elevated blood pressure. This happens through the activation of specific brain regions like the paraventricular nucleus or PVN in the hypothalamus, which then communicates directly with these crucial brainstem areas, creating a cascading effect that impacts cardiovascular health.
So, all these pieces of research are starting to paint a much clearer picture, showing that the brain isn't just a passive observer when it comes to blood pressure, it's an active central regulator and sometimes, perhaps even a direct instigator of the problem. This new PFL discovery seems to be a significant puzzle piece in that growing understanding.
Indeed, it's really connecting some crucial dots. What's particularly fascinating about this PFL region is its direct connection to forceful exhalations. Unlike a passive exhalation where you just breathe out without effort, forceful exhalations actively engage your abdominal muscles, creating pressure. The study suggests that specific breathing patterns, especially those that involve strong abdominal muscle contractions, could directly contribute to elevated blood pressure through this very mechanism.
That's a profound connection, Maya, because it links a very common everyday action, breathing, to a major health issue. This finding actually aligns remarkably well with existing knowledge we have about how breathing influences blood pressure. We've been hearing about deep breathing exercises for years as a way to manage stress and improve health, but now we might have a specific neurological explanation for why they work so effectively.
Exactly. Deep breathing exercises are widely recognized and recommended for their ability to lower blood pressure. And now we have a clearer idea of the neural pathways involved. They achieve this by promoting relaxation, which reduces overall stress, enhancing oxygen flow throughout the body, calming the entire nervous system, and helping to regulate heart rate. It's a holistic effect, but the brainstem seems to be a central player.
So, if forceful exhalations through the PFL can raise blood pressure, then it makes intuitive sense that certain breathing techniques, particularly those focusing on controlled, prolonged exhalations, would work to lower it. These techniques essentially help shift the body from that fight or flight sympathetic state, which is characterized by heightened alert and increased blood pressure, to a much calmer rest and digest parasympathetic state.
Absolutely. It's about consciously hacking into our autonomic nervous system. Specific practices like 4-7-8 breathing, which involves inhaling for 4 counts, holding for 7, and exhaling for 8, are often recommended. Then there's box breathing, where you inhale, hold, exhale, and hold, all for the same count, creating a square pattern, and also alternate nostril breathing, a traditional yogic technique. All of these methods typically involve a prolonged exhalation phase.
And it's that prolonged exhalation that seems to be key, isn't it? The theory is that by extending the exhalation, you're leveraging the nervous system's automatic response to decrease heart rate and promote blood vessel widening, effectively counteracting the constriction that the PFL might otherwise trigger. It's a fascinating dance between conscious control and unconscious physiological responses.
It truly is. This new understanding carries really significant implications for how we approach and develop future hypertension treatments. The discovery of the PFL region suggests that entirely new therapeutic strategies could be developed to target this specific brain region directly, or perhaps indirectly through related oxygen-sensing cells located in the neck, which are known as carotid bodies.
Targeting the brain directly with drugs is notoriously complex and challenging, primarily because of the potential for widespread and often unwanted side effects due to drugs affecting multiple brain regions. However, modulating these carotid bodies might offer a much safer and more localized approach to calm this specific brainstem circuit, potentially offering a more precise intervention without the broad systemic impact.
That's a crucial distinction for drug development, Alex, because precision is everything when it comes to the brain. This new mechanism could also potentially explain why a substantial portion, approximately 40% of individuals with hypertension, do not respond adequately to existing medications. If their hypertension is primarily driven by this brain-based trigger, then medications targeting heart function or blood vessel dilation might simply not be addressing the root cause.
40% is a huge number of people, Maya. That's a significant population for whom current treatments are insufficient, leaving them vulnerable to the serious health consequences of uncontrolled high blood pressure. This finding gives us hope for those individuals, suggesting that their drug-resistant hypertension isn't a dead end, but rather a problem that might have a very specific neurological solution.
And the findings are particularly relevant for conditions like sleep apnea, where carotid bodies become overactive when breathing stops during sleep. We know that sleep apnea is a major risk factor for hypertension. In animal models of neurogenic hypertension, which is hypertension induced by chronic intermittent hypoxia, essentially mimicking sleep apnea, inhibiting these specific neurons actually normalize blood pressure. This draws a very clear line between this brain mechanism and a common clinical problem.
That connection to sleep apnea is incredibly powerful and adds another layer of clinical relevance to this research. It highlights how interconnected our bodily systems are, and how disruptions in one, like breathing during sleep, can have profound effects on another, like blood pressure regulation, all mediated by these specific brain circuits.
Now, let's talk about the sheer scale of the problem globally, because hypertension isn't a niche issue, it's a massive public health crisis. The World Health Organization reported in 2025 that an estimated 1.4 billion people worldwide suffer from hypertension. And what's even more alarming is that only 1 in 5 successfully manages their condition. That's a staggering statistic.
It truly is. In countries like Brazil, where some of this research was conducted, hypertension affects about 30% of adults, and it's important to remember that the definition of normal blood pressure has shifted over time. A reading of 12 by 8 or 120/80 millimeters of mercury is now considered pre-hypertension, with truly normal blood pressure defined as below this threshold. This means even more people are falling into the at-risk category.
So, while this study identifies a fascinating and crucial mechanism, it doesn't yet provide specific relative or absolute risk statistics for individuals based directly on their breathing patterns. However, if this brain-based trigger contributes to hypertension in a significant percentage of patients, particularly those with drug-resistant forms, it flags a previously underestimated absolute risk factor rooted in neural control. The potential for this mechanism to drive 40% of treatment-resistant hypertension really represents a substantial population for whom current treatments are simply not enough.
That's a very important nuance to highlight, Maya. We're talking about identifying a mechanism that could explain a significant portion of existing hard-to-treat cases rather than a new risk factor that applies broadly to everyone in the same way. It's about refining our understanding of why some people develop hypertension and why it's so difficult to manage for others.
And regarding the study's credibility, it's worth noting that the research was a collaborative effort involving institutions like the University of Auckland in New Zealand and the University of Sao Paulo in Brazil. Funding for the Brazilian component of the research appears to have come from the Fundação de Amparo à Pesquisa do Estado de São Paulo, or FAPESP, which is a reputable research funding agency. Knowing the funding source and the institutions involved helps us gauge the rigor and resources behind the study.
Absolutely. Transparency in funding is always important for scientific integrity. Now, as with any groundbreaking research, it's essential to look at it from all angles to steelman both sides of the argument. So, let's first consider the strongest arguments for why this discovery is truly a game changer in the field of hypertension.
From the game changer perspective, this study represents a profound leap in our understanding of hypertension by pinpointing a direct, brain-based causal mechanism right there in the brainstem. The ability to normalize blood pressure simply by inactivating the PFL region in animal experiments provides incredibly compelling evidence for its pivotal role, offering a novel and powerful explanation for those challenging cases of hypertension that have been resistant to all conventional treatments for so long.
It absolutely opens up exciting new therapeutic avenues, moving beyond the current limitations of medications that often only address symptoms or downstream effects. We could potentially develop highly targeted treatments that modulate specific neural circuits or even peripheral sensors like the carotid bodies. This promises more effective, personalized care for a huge segment of the population that currently struggles to manage their condition. It fundamentally shifts our perspective, Maya, emphasizing the brain's central command over cardiovascular function and linking a seemingly simple physiological action, breathing, to a major global health crisis.
That's a powerful summation of its potential impact. It's not just another piece of the puzzle, it feels like discovering a new control panel for a complex machine we thought we understood. But now let's steelman the other side, the hold your horses perspective, which advocates for caution and nuance in interpreting these findings, as is always important with early stage research.
Right. So while promising, it's crucial to acknowledge that the primary findings of this study were derived from animal models, specifically mice and rats. The translation of these findings directly to complex human physiology and disease requires extensive further research, rigorous validation, and of course, large-scale clinical trials in humans before we can definitively say how applicable this is across the board. Animal models are a vital first step, but they are not the final word.
That's a really important caveat. Hypertension is a notoriously complex and multifactorial condition, meaning it's influenced by a myriad of genetic, environmental, and lifestyle factors, all interacting in intricate ways. While this brainstem mechanism is undoubtedly significant, it's highly probable that it's just one crucial component within a much broader network of influences. It may not be the sole or even the primary cause for every individual who has hypertension.
And let's not forget that the proposed therapeutic targets like directly modulating the PFL or the carotid bodies are still in very early stages of exploration. They will require rigorous testing for safety, efficacy, and long-term outcomes in humans before they can even be considered viable treatments. It's a long road from a scientific discovery in a lab to a medication available in a pharmacy.
Furthermore, while the study highlights a very specific neural mechanism for how breathing patterns can affect blood pressure, the general concept that stress and certain breathing techniques can influence blood pressure isn't entirely new. Deep breathing exercises have long been recognized and recommended as a complementary approach to managing blood pressure and stress. So, in a way, this research provides a precise neural explanation for a known phenomenon, rather than an entirely novel concept of influence. It's a deeper understanding, not necessarily a completely new effect.
That's a very fair point, Maya. It's important to distinguish between discovering a mechanism for something we already observed and discovering an entirely new phenomenon. This study gives us the how and the why for a piece of the hypertension puzzle that was previously understood more broadly. It adds incredible scientific rigor to practices that many people have been using for centuries.
Exactly. So, while it's incredibly exciting and definitely offers new hope, particularly for those with drug-resistant hypertension, it's also crucial to maintain a balanced perspective. It's a powerful piece of evidence, but it fits into a much larger, ongoing scientific narrative about a very complex disease. It means we should definitely keep an eye on future research building on these findings.
I think that balanced view is essential. This new discovery about the PFL region in the brainstem really underscores how intricate our bodies are and how much we still have to learn even about common conditions like high blood pressure. It reminds us that sometimes the answers to our biggest health challenges might be hidden in plain sight, deep within our own biology.
And it certainly makes me think a lot more about my own breathing patterns, Alex. Knowing that something as fundamental as how I exhale could be influencing my blood pressure without my awareness is a powerful motivator to pay more attention to those deep breathing techniques we discussed. It's a simple, accessible tool that now has a much stronger scientific backing, at least in terms of its potential impact.
It certainly adds a whole new dimension to mindfulness and breathwork, doesn't it? It shifts it from being just a stress reduction technique to potentially a direct modulator of cardiovascular health with a specific neural pathway identified. It will be fascinating to watch how this research evolves and what clinical applications emerge in the coming years.
I'm definitely going to be following Professor Payton's and Professor Morias's work closely. This kind of research has the potential to genuinely transform how we prevent and treat a condition that impacts so many lives worldwide. It's a powerful reminder that our understanding of the human body is constantly expanding, and there's always more to learn about the things we know nothing about.